Welcome to the first lecture in source coding. In this course, we'll see the theory and algorithms behind data compression. So what do we understand by compression? Broadly speaking, the problem of compression is to design algorithms in order to save space or bandwidth. So we have a file, it could be either a text file or an image or maybe a database, and in order to save space, we want to somehow transform it into something else which takes less space. But at the same time, we want this transformation to be to sort of preserve all the information that is there in the original file. Right? So we want to be able to get back the original information from this compressed file. So data compression basically involves the design of two algorithms, one which is called a compression algorithm. Right, so the problem of compression algorithm takes your raw file, which could be either text or image or a database, and then outputs a binary file, which is a compressed file. So this compressed file should take less space, should occupy less space than the raw file. But at the same time, we also want to be able to get back the original file or get back the information from in the original file from the compressed file. So decompression is the process of recovering the information, the original information from the compressed file. When I talk about data compression, I'm basically talking about both the compression and the decompression algorithm. So let us sort of put this more formally, right? So we're given a file, or maybe which has n symbols or n characters. I'll call this xn. So xn is my raw file, sometimes called the source sequence. So it's a sequence of n characters, and so this could be a sequence of bits, it could be a sequence of words. So if you have English text, it could be you could consider it as a sequence of n words, or as a sequence of n sentences, or as a sequence of n ASCII characters. Right? So all of these are valid representations or interpretations of the source file, and depending on which interpretation you use, you'll get a different decompression and compression algorithm, and the amount of complexity for decompression and compression would depend on really how you model this source file or raw file. So we will try to completely abstract all of that out. We won't really care whether this is a text file or whether this is an image. So if it's an image, then you could consider this as a sequence of RGB values. If it's a video, you could consider it again as a sequence of images, right? Because each frame is basically an image. If it's audio, then you could treat this as a sequence of the amplitudes. It's a sequence of amplitudes at each time instant, right? So there are, but at least for our purposes, in order to design compression and decompression algorithms, we'll try to use or we'll try to develop models which are agnostic to what the file exactly is. So we won't care about the meaning of the source itself, but what we will be interested in is the statistics of the source. Right? And what do I mean by that? So we have a raw file, which is a sequence of n symbols. We'll model this as x1, x2 up to xn, where each xi comes from some set which I'll call the alphabet or the source alphabet. Right? So if the file is an ASCII file, then the alphabet could be the set of all ASCII characters. If it's a binary file, then the alphabet is simply the set 0, 1. If it's an image file, then the alphabet is all possible RGB values, and so on. Right? If it's an English file, then you could say that each maybe it's a sequence of words or a sequence of sentences, right? So the alphabet could be either the set of all possible words in the English language or the set of all possible English sentences, right? So we'll develop a mathematical model which doesn't really care about the meaning behind the raw file. So it doesn't care what meaning the raw file contains, but we will take into account the statistics. So we will assume that the sequence xn is actually a random quantity, and it is distributed according to some distribution pxn. Right, so it has some valid distribution, and for most parts of the course we will assume that this distribution is known. Now this is not a valid assumption in practice, and we'll see later on how we can remove this. So even without knowing the distribution, you can still construct good compression decompression algorithms. So implicitly we will assume that both the compressor and the decompressor know the statistics of the source. In fact, we'll see that one way to sort of solve this problem is to simply estimate the distribution, estimate the statistics, and store it as a header of the compressed file. So this is available both for the compressor and the decompressor. But more about that later. So the source for us is going to be just a sequence of characters from the alphabet. And the compressor is going to be an algorithm which takes this sequence of characters and outputs a binary sequence ck. So this is what we'll call the code word or the compressed sequence. Okay, so this is going to be a sequence of k bits, where k is the length of the code word or the length of the compressed sequence or the size of the compressed file. Okay. Now it's not enough to just compress it. We also want to be able to recover the information about xn from ck. So the decompressor or the decompression algorithm takes as input the compressed sequence and outputs an estimate or a reconstruction of the source. Okay, so hopefully xn hat is some faithful representation of xn. So if you want to put this abstractly, then the compressor is going to be an algorithm which takes a sequence of n characters and outputs a sequence of bits. So here 0, 1 star basically represents the set of all possible binary sequences of all possible lengths, and the decompressor basically takes a binary sequence and outputs an estimate of the original of the source. All right. So this is a mathematical representation of, or a mathematical description of, the data compression problem. For most parts of this course, we will study what I call traditional compression. So what do I mean by traditional compression? So traditional compression involves compression of objects like text files or images or audio or video. And I call this traditional because a good model for these kinds of data is basically a stationary and ergodic kind of a model. So xn is basically stationary. It's a random process which is basically a stationary and ergodic process. And moreover, finally what we're interested in is getting back the original file. You compress the file, you get a compressed sequence or a code word, and then your goal is to reconstruct the entire file. And these are good for classical applications. And today we know very good algorithms. So for text, it is known for say English text, it is known that algorithms such as 7-zip are optimal, or at least close to optimal. You can't really do much better than 7-zip for arbitrary text files. For images, JPEG does a pretty good job, and audio and video, we have the MPEG standards, which are almost optimal compression algorithms. Now, in recent times, we've seen non-stationary kind of data, non-stationary or non-ergodic type of data, for which traditional compression algorithms don't work very well. And these are still, designing good compression algorithms for these applications is still work in progress. So we have the so-called modern compression problems, which could be compression of big data or graphs. So a lot of modern types of data can be represented in the form of a graph. So this is not a sequence anymore, but the graphical structure also carries a lot of information. Traditional compression algorithms can be broadly classified into multiple types depending on how good of a reconstruction we want. Now, depending on the application, we may want that the reconstructed file xn hat should be exactly the same as the original file. We want absolutely no error. So this, for example, if you're trying to zip a particular file, if you have a text file and in order to save space on your disk, you want to compress it, then ideally you want to get back the original text file. You don't want any kind of errors in the file. Right? So this is what I call lossless compression, where we make absolutely no errors. Also, at times, if you want to transmit files across a network or across a noisy medium, then the medium introduces errors. It introduces errors anyway. So it's okay if the compression algorithm also makes a small number of errors. So ideally, we want the probability of the reconstructed file being different from the original file to be something very small. So these are what I call almost lossless compression, and broadly speaking, we'll be seeing 1 and 2 under the umbrella of lossless compression. Now, at times we don't want the original file exactly, but as long as it is roughly the same as the original file, it's good enough. So for example, if you want to share a picture on Instagram or WhatsApp, then you don't really care whether it's the exact, whether pixel by pixel it's the same file, it's the same image. Even if the resolution of the compressed image is slightly worse than the original image, it's good enough, because once you see the sort of the low res image, you still get to know what's going on. Right? So this is what I call lossy compression, where you tolerate some amount of distortion. Right? So we have lossless compression, we have almost lossless compression, and we have lossy compression. And we'll sort of set up each of these problems in a little bit of detail.